Welcome to this video on hydrogen fuel cells. This is cutting-edge technology that could really pave the future for transportation and energy production in our future. Here we have a graph. You can see we have wood, coal, oil, natural gas, hydrogen. These, what do they all have in common? They're all fuels. They're all fuels that we've used throughout history, fuels that we've used in the production of heat and transportation and so forth throughout history. It's interesting to note that as fuel use has developed through the time, the percentage of hydrogen content in that fuel has increased. Many engineers see it as a natural progression that the fuel of the future will be hydrogen. Because after all, hydrogen is 100% hydrogen. Hydrogen also is the most plentiful element in the universe. All right, so if we could use it, it sounds excellent, right? Well, the two principal reactions in the burning of a hydrocarbon fuel are the formation of water and the formation of carbon dioxide. So that's going to be the case in wood, coal, oil, natural gas. As hydrogen content in a fuel increases, the formation of water becomes more significant, resulting in proportionately lower emissions of carbon dioxide, which we're all concerned about. So a very range of organizations, from energy companies to automobile manufacturers, have been working to develop fuel cells and the accompanying infrastructure that goes along with them. As technology has progressed, so has the production of power. All right, 19th century, that was the century of steam and fueled the Industrial Revolution. The 20th century was the century of the internal combustion engine, and we saw transportation come to the masses. Well, hopefully the 21st century might be could be the century of the fuel cell. So we need to study it. So let's take a look at the history of fuel cells. Well, the first fuel cell that was really effectively developed was in 1839 by Sir William Grove. He was a Welsh scientist and lawyer. The principle was discovered by accident. He was performing an electrolysis experiment when he disconnected the battery from the electrolyser and connected the two electrodes together. He noticed that a current flowed in the opposite direction, consuming the gases of hydrogen and oxygen. He called this device a gas battery. His gas battery consisted of platinum electrodes placed in test tubes of hydrogen and oxygen, immersed in a bath of dilute sulfuric acid. It generated a voltage of about 1 volt. So, significant developmental work on fuel cells began again in the 1930s by Francis Bacon, a chemical engineer at Cambridge University. In the 1950s, Bacon successfully produced the first practical fuel cell, an alkaline fuel cell. It used an alkaline electrolyte instead of the dilute sulfuric acid. The electrodes were constructed of porous sintered nickel powder so that the gases could diffuse through the electrodes to be in contact with the aqueous electrolyte on the other side. This greatly increased the contact area between the electrodes, the gases, and the electrolyte, thus increasing the power density of the fuel cell. In addition, the use of nickel was much less expensive than that of platinum. An assistant can be seen in this photograph mounting a plate onto the side of Bacon's fuel cell stack. The Bacon fuel cell was modified by NASA in the 1960s as a method to supply onboard drinking water as well as electricity for the astronauts aboard the Apollo space missions. An alkaline fuel cell was also used in the Space Shuttle Orbiter. Space Shuttle Orbiter fuel cell has been produced since the 1970s by International Fuel Cell USA. It produces 12 kilowatts of electricity, weighs about 202 pounds, and occupies a space of about 4.6 cubic feet. All right, well, they've gotten a lot smaller since then. Alkaline fuel cells offer the advantages of high voltage output per cell. Each of the cells that were on the space shuttle has an operating voltage of about 0.875 volts, and that non-precious materials can be used as electrodes. The primary disadvantage of alkaline fuel cells for terrestrial applications is that of carbon dioxide poisoning the electrolyte. Carbon dioxide, present in both the atmosphere as well as in the reformate, the hydrogen-rich gas produced from the reformation of hydrocarbon fuels, reacts with the hydroxide ion in the electrolyte to form a carbonate, thus reducing the hydroxide ion concentration in the electrolyte. This reduction in hydroxide ion concentration inhibits the ability of the fuel cell to generate the current. Because of the complexity of isolating carbon dioxide from the alkaline electrolyte for terrestrial applications, most fuel cell developers today have focused their attention on developing new types of fuel cells using electrolytes other than that of alkaline. In the mid-1980s, Ballard Power, based in Vancouver, British Columbia, and working on a contract from the Canadian Department of National Defence, made significant breakthroughs in fuel cells. Working with Johnson Matthey in the UK, they developed PEM fuel cells, which had a significant increase in power density. From these breakthroughs, it was recognized that fuel cells could be made small, powerful, and inexpensive enough to replace conventional power technologies. The California Low Emission Vehicle Program of the California Air Resources Board, or CARB, has been a large incentive for automakers to develop fuel cell automobiles. This program required that back in 2003, 10% of passenger cars delivered for sale in California must be zero-emission vehicles, called ZEVs. Automobiles powered by fuel cells meet these requirements. To date, 7 of the world's 10 leading auto manufacturers are building prototypes and plan to introduce fuel cell automobiles in the near future. The Nicar 5 shown here was a prototype automobile built by Daimler Chrysler, back when Daimler and Chrysler were together. This automobile is fueled with liquid methanol and has a top speed of over 90 miles per hour, 150 kilometers per hour. In forthcoming years, there are plans for buses, trucks, trains, all powered with fuel cell engines. And we're starting to see some of that happening today. 30 buses are going to be commercially introduced in 10 European cities beginning in 2002. Electrical energy demands throughout the world are continuing to increase. In Canada, the electrical energy demand is growing at an annual rate of approximately 2.6%. In America, the electrical energy demand is growing at an annual rate of a little bit less, 2.4%. In developing countries, though, electrical demand is growing at an annual rate of almost 6%. How can these demands be met responsibly and safely? There are many problems associated with the building of new power plants, both financially and environmentally. Fuel cell distributed power stations provide an excellent solution. Fuel cell distributed power plants can provide high quality, reliable power. Depending on the type of fuel cells used, power plants produce little or no emissions. Shown here is a prototype fuel cell distributed power plant recently developed by Ballard Power. This particular unit was commissioned for the BC Hydro Grid. It provides 250 kilowatts of electricity and about the same amount of heat fueled from natural gas. This is enough power to provide heat and electricity to a community of about 50 homes, for example, or to a hospital or to a remote location school. 85 kilowatt Ballard fuel cells are powering 12 large buses in China right now, and they also have a deal with Toyota to sell fuel cells to other auto manufacturers. Fuel cell power plants are being developed by lots of different manufacturers to provide electricity and heat to a single family home. Fueled by either natural gas or propane, these fuel cell power plants will be able to power a home independent of the grid. Plug Power, based in Latham, New York, they developed a new fuel cell power plant that supplies 7 kilowatts of electricity and heat, using either natural gas or propane as the fuel. That is enough power to supply the electrical demands of a modern energy-efficient home. Initially, these fuel cell power plants will be grid parallel. Eventually, they'll be grid independent. Plug Power plans to commercially introduce this home power plant distributed through General Electric. Several manufacturers are developing portable fuel cell power supplies. These power supplies can provide anything from a few watts up to several kilowatts of electricity. Portable fuel cell power supplies will be an alternative to conventional batteries for many applications. Applications include laptops, mobile phones, remote road signs, and lighting. Portable fuel cell power supplies have several advantages over conventional batteries. Primary advantage is that of energy density. Fuel cells can provide a higher energy density by both volume and weight. Thus, fuel cell portable power packs can be lighter and supply power for a longer period of time than that of a conventional battery. In addition, the storage losses for hydrogen fuel cells are practically non-existent. Whereas conventional batteries slowly discharge their power over time, fuel cells powered by hydrogen can maintain their charge almost indefinitely. The third advantage is that the storage capacity of rechargeable batteries decreases as a function of the number of cycles of charge and discharge, such that they will eventually have to be replaced. Fuel cells will maintain their power output almost indefinitely. This particular fuel cell is a prototype 40-watt PEM fuel cell by Heliocentrics, powering a remote blinking lamp. The fuel cell is contained in the upper part of the unit. The lower part of the unit contains a metal hydride storage cylinder containing the hydrogen. Motorola Labs and the Los Alamos National Laboratory are co-developing portable fuel cell technology using direct methanol fuel cells. Company officials say these fuel cells, including a canister of methanol, will supply 10 times the energy of a rechargeable battery of equivalent size. Thus, mobile phones, for example, will apparently be able to remain on standby for a period of over a month. When the methanol in the canister is consumed, a new canister can easily be inserted. With the advent of this process, recharging batteries will no longer be necessary. Motorola expects these fuel cells to be commercially available in 3 to 5 years. Well, that's a problem. If you guys don't have to charge your batteries on your phones, you'll never stop texting. Fuel cells are classified by the type of electrolyte they use. Different electrolytes operate at different temperatures. Low temperature fuel cells, including the alkaline fuel cell, AFC, the proton exchange membrane fuel cell, PEMFC, and the phosphoric acid fuel cell, PAFC. All these fuel cells use hydrogen as a fuel. This hydrogen can be extracted from natural gas, biogas, methanol, or propane by the process of reformation. The hydrogen can also be created through the electrolysis of water. High-temperature fuel cells include the molten carbonate fuel cell, MCFC, and the solid oxide fuel cell, SOFC. These fuel cells offer the advantage that they can use either natural gas or untreated coal gas as a fuel, directly without the use of a reformer, through a process called direct internal reforming. The sixth type of fuel cell is the direct methanol fuel cell, DMFC. It is also a low-temperature fuel cell, but it can use methanol as a fuel directly without the need of reforming. The primary limitation to the direct methanol fuel cell is that the rate of reaction on the anode is very slow. This results in a very low operating voltage output. For certain applications, portable power for example, the direct methanol fuel cell may be ideal. A fuel cell is a device that through an electrochemical process converts hydrogen and oxygen directly into water. In this process, energy is released in the form of electricity and heat. The chemical process is electrolysis in reverse. In the PEM fuel cell, the proton exchange membrane fuel cell, hydrogen molecules are oxidized at the anode to positively charged hydrogen ions. Protons releasing electrons to the cathode via an external electrical load. That means that those electrons are going to flow from the anode to the cathode. That flow of electrons is electricity, and we can put it to work. We can make it do work for us. The protons diffuse through an ion-conducting membrane. This ion-conducting membrane will allows the protons to move through, but not the electrons. So the electrons have to take the long way around. And that long way around travels through, let's say, a motor or a light, and in the form of electrical current. The cathode, oxygen Let's try it again. At the cathode, oxygen combines with the electrons and the protons to form water. The overall reaction is hydrogen plus oxygen producing water. In this diagram, we can see the various components of a simple fuel cell. A single cell consists of two gas-filled flow plates, one for hydrogen and one for oxygen, separated by a membrane electrode assembly, abbreviated MEA. Field flow plates contain channels to ensure that the gases are in contact with as much of the MEA as possible. As can be seen in the diagram, hydrogen molecules enter on the anode side of the cell, while oxygen enters on the cathode side of the cell. In a reduction reaction, the hydrogen molecules release its electrons, which flow from the anode electrode through the external electric load to the cathode electrode. It is this flow of electrons which we observe as electricity. The hydrogen protons flow through the ion conducting membrane to the cathode. At the cathode, they combine with the oxygen molecules and the free electrons to form water. The fuel cell has electrochemically converted hydrogen and oxygen gases into electricity and water. That is an excellent product. The MEA consists of two porous carbon cloth electrodes bonded to each side of a polymer electrolyte membrane. This material, the electrolyte, allows the conduction of hydrogen protons from one side of the membrane through to the other. At the same time, it prevents oxygen molecules from flowing in the reverse direction. On the electrodes are nano-sized particles of platinum. The platinum acts as a catalyst for the redox reaction to take place. Initially, the hydrogen molecules are chemically absorbed onto the platinum surface, forming hydrogen-platinum bonds. Platinum is unique in that it has the ideal bonding strength to both break the hydrogen molecule bond to form the hydrogen-platinum bonds, while being able to release the hydrogen, allowing the redox reaction to proceed. A fuel cell, therefore, supplies a current much the same way as a battery. However, unlike a battery, a fuel cell can provide electrical power indefinitely, as long as hydrogen and oxygen are being supplied. The membranes of a fuel cell is between 50 and 175 microns thick. That's about the thickness of 2 to 7 sheets of paper. It is produced in sheets which can be cut into the required size. The electrolyte membrane consists of polytetrafluoroethylene chains, commonly called Teflon. On the Teflon chains are side chains ending with sulfonic acid, HSO3. A close-up view of the membrane material shows spaghetti-like long chain molecules with clusters of sulfonate side chains. An interesting feature of this material is that whereas the long chain molecules are hydrophobic, meaning they repel water, the sulfonate side chains are highly hydrophilic. They attract water. Hydrophobic versus hydrophilic. The hydrophilic regions absorb large quantities of water. Within these hydrated regions, the H plus ions of the sulfonic acid are able to move, creating the ability for this material to transfer the H plus ions, the protons, from one side of the membrane to the other. For this reason, the hydrated regions must be as large as possible. Working through the calculations, we see that the ideal cell voltage at room temperature is 1.23 volts. However, as the fuel cell heats up to an operating temperature of about 80 degrees Celsius, the ideal cell voltage drops to 1.18 volts. More factors are involved in practical fuel cells, which reduce the cell voltage considerably. We can see here the characteristic curve of the fuel cell. The characteristic curve of a fuel cell is the relationship between the current density and the cell voltage. Notice a sharp fall from the ideal cell voltage immediately following open circuit. This is followed by a somewhat linear decline in cell voltage. This is followed by a rapid drop-off in cell voltage. The primary factors affecting the curve are listed below. Each of these losses contributes to the decline in cell voltage. Activation losses are a result of the slow speed of the reaction taking place. Fuel crossover in internal currents is a result of fuel which crosses through the membrane, not contributing to the chemical redox reaction, thus not contributing to the production of electricity. Ohmic losses are a direct relationship to the combined resistance of the various components within the fuel cell circuit. This includes the material of the electrodes, the membrane, and the various interconnections. Mass transport, often called concentration losses, is a result of the reduction of the concentration of hydrogen and oxygen on the electrode surface. This is due to the failure to transport the required gases to the electrode surfaces. By careful design in all of the components involving science, engineering, and the technical trades, these losses can be minimized, resulting in fuel cells that are efficient and deliver high power density. The second graph of the power curve is a plot of the relationship between the current density and the power output of the cell. The maximum power point of a fuel cell can be determined either by plotting it on a graph paper, as shown here, or by determining the equation of the curve and differentiating that equation. It's interesting to compare the various methods available to date for the storage of hydrogen. We can see here that for 1 kilogram of hydrogen in a compressed gas cylinder requires a volume of 56 liters. Or, as liquid hydrogen, not including the necessary equipment, only requires 14 liters. Now, if you have the hydrogen stored in a magnesium metal hydride container, you can get that volume down to 9.9 liters. Reformers convert a hydrogen-rich fuel such as natural gas, methanol, or even gasoline into pure hydrogen, plus the emission of carbon dioxide. They work via a catalytic process combining the fuel with water vapor at a high temperature. The result is fuel cell automobiles are able to carry liquid fuels, and fuel cell stationary power plants can use natural gas or propane. For the immediate future, as long as fossil fuels are available, the use of reformers is the most cost-efficient method for producing hydrogen. As long as the sun shines, the wind blows, or the rivers flow, there can be clean, safe, and sustainable electrical power, where and when required, with a solar hydrogen energy system. Fuel cells are efficient. As fuel cells convert hydrogen and oxygen directly into electricity and water, there is no combustion in the process. As a result, the efficiency is high, between 50 and 60%, about double that of an internal combustion engine. Fuel cells, of course, are clean. If hydrogen is the fuel, there are no pollutant emissions from a fuel cell, only the production of pure water. In contrast to an internal combustion engine, a fuel cell produces no emissions of sulfur dioxide, which can lead to acid rain, oxides of nitrogen, which produces smog, or particulates, grit, and dust. If methanol or natural gas is the fuel, there's an emission of carbon dioxide. However, as the efficiency of fuel cell is higher than that of an internal combustion engine, the emission of carbon dioxide is proportionately lower. Fuel cells are quiet. A fuel cell itself has no moving parts. However, a fuel cell system may have a few moving parts, including pumps and fans. As a result, a fuel cell produces electrical power virtually silently. Many hotels and resorts in quiet locations, for example, would like to replace diesel engine generators with fuel cells for both main power supply or for backup power in the event of a power outage. Fuel cells are modular. That is, fuel cell stacks of varying sizes can be theoretically combined together to meet a required power demand. Fuel cells are environmentally safe. They produce no hazardous waste products, only the production of water. Fuel cells provide the opportunity to produce a sustainable source of electrical power, If fuel cells get their hydrogen from renewable energy sources, such as solar, wind, hydro, or biological methods, they can provide a sustainable source of electrical power. So, we do have a responsibility to our planet. We are its custodians. So we want to do what's best to help with that. All right, thank you for watching this video. It was an introduction to hydrogen fuel cells.